All right, so we are going to get started. We're going to talk about some very basic concepts with electric circuits. Let's go ahead and just jump on in. So the first thing that we're going to talk about is electric current. So current is given to us with a couple of different things in mind. We know that there are charges that move through a conductor, and which we are calling wires now. The wires in a circuit are conductors. And so that we have a movement of charge, and we know that charge has always been given to us in terms of Q. So we also have this new letter in here that we have an I. So current is really just a rate at which charge is moving through the wire. So we have the amount of charge per unit time, which gives us a unit of a coulomb versus, or coulomb over a second. So the unit of charge is a coulomb divided by a second, and that gives us the unit for current. But a coulomb per second is something that we've named after a scientist, a physicist, whose name was Andre Ampere, and so we call it the amp. So you might have heard this unit before, you know, so many amps of current, so many amps of electricity, and this is where the unit comes from. But an amp is really a coulomb per second, and this is our measure of how much current. So I talked earlier about giving you what the standard for a coulomb is. And this is really where the standard comes from. A coulomb is the amount of charge that can flow through a wire every second. So 1 coulomb is equal to 1 second if you have 1 amp of current. And the amp is really related to other things as well. So 1 amp is going to be 1 coulomb for every second. That's where the coulomb comes from. That's why we have a really large charge for a coulomb, really large unit there. But we need to talk about how things flow through a wire. Benjamin Franklin, who did a lot of things with electricity, thought that it was really the positive charges that moved through a given conductor. So he did everything in terms of positive charges. Well, we know now that the positive charges are the protons, and we know those are locked away into the nuclei of actual atoms. But electrons, however, electrons are the ones that are able to move. They have more mobility. So a current that is made up of electrons that is flowing to the left, we actually call it a current that is flowing to the right, a positive current. So we take the current the way that the positive charges would go. This is very similar to how we did electric field, right? Electric field is the direction that a positive charge would go or would have a force on it given the configuration of charges. So we always talk about it in terms of positive charges. What direction would the positive charge go? So if we have a circuit that has a battery in it and a light bulb, and this is the positive end and this is the negative end, the direction of current that we would draw in here would be coming out of the positives and going into the negative, kind of similar to the electric field, right? But we know that the actual charge is coming from the negative side. The electrons are coming from the negative side and going the opposite direction. But we are going to, by convention, talk about current as going the way that a positive charge would go. Okay, and this is really, we had a choice, and Benny Frank made that choice a long time ago, and we've just kept with his choice. So we're going to go the direction that a positive charge would go. Just a reminder that you can always pause, rewind, re-listen whenever you need to. Okay, so what is actually making these charges go through the wires? What's causing this flow of electricity? Well, people originally thought that there was a force. There was a force that forced the protons, or the positive charge, that moved through a wire. We now know that there's no actual force. It's really just potential energy, right? Going from a high potential energy down to a low potential energy. So same kind of hill type deal. A ball doesn't want to stay at the top of the hill. It wants to roll down given the possibility. And that's really what's going on with electron charges, or current for that matter. It's going from an area with high potential down to an area of low potential. So it's falling through the wires in an energy type sense. But there is no force that's really pushing it along other than maybe the electrostatic force. But the electromotive force, this EMF that people talked about, was what they thought pushed current through a wire. We know that's not the case, but we've kept the term electromotive force to talk about things that can generate electricity. So a battery is an EMF. A generator here is an EMF, but they get their energy from other things, right? These are both really chemical processes. We have chemical battery acid and gasoline in here, so they convert their chemical energy into electrical energy. This one is actually a little bit more in depth. It goes from chemical energy to mechanical energy, which goes into electricity, and we'll talk about the way that goes later, probably next unit. So the big thing that we're going to talk about in this unit is called Ohm's Law, named after a guy named Ohm. I believe you still pronounce that as George. So it's George Simon Ohm, and he talked about the relationship between voltage and current. And he gave a couple of equations, well, really just one equation. He said that the resistance in a wire, so this R, how much impedance is also another word for this, how much resistance is going to be fought, the current's going to have to fight in a wire is given by the ratio between the voltage and the current. So the ratio of voltage to current is going to be the resistance in a wire. Most of the time I remember in this form of V is equal to IR. Right? This is easier for me to remember. So voltage is equal to current times resistance. So this has given us that a volt is, just give me a second. A volt is equal to an amp times some other unit that we need to figure out. Well, over here, resistance is given to us as volts divided by amps, right? Voltage divided by current. Well, resistance is given a new unit, and it is another Greek letter. A volt divided by an amp is given to be an ohm, O-H-M, and this is the Greek letter omega. So ohm. So how is one current or 1 amp of current defined? Well, if you have a potential difference of 1 volt and 1 amp of current goes through that circuit, then the resistance is 1 ohm. Or you can talk about in terms of 1 volt and 1 ohm gives 1 amp of current. So all this is really standardized to circuits. Now resistance is really just the opposition to the flow of charge. This right here is a resistor. We're going to be dealing a lot with resistors as we go through this unit. And you notice how there's 3 different colors here. There's an orange, there's a black, and there's a brown. Well, there's a specific, oh, there's actually 4. There's a gold one here. There's a way that you read these particular colors, and you're going to have to know how to do that as we go through some of the labs that we're going to do. A resistor is basically a whole bunch of crud that gets put in the way of current. Current wants to flow through here, but it has a hard time flowing through this carbon that gets thrown in its way. And depending on how much is in here and how big the resistance is, then there could be a major opposition to the flow of current. So the resistor color code is given over here. And if we go over and take a look at what we have an orange. So orange is 3. We have a black. Black is 0. And we have a brown. Brown is 1. Then that gold on the other hand is 5%. We'll come back to that here in a second. So to read this, though, we have to read it in a specific way, and that specific way is digit-digit multiplier. So if we have orange is the first digit, so that's 3, black is the next digit, that's 0, and we have a multiplier, times 10 to the something, and that's a brown, so times 10 to the 1. Well, we have 30 times 10 to the 1, which is just 10. So when you do that, you have 300. And that's 300 what? 300 ohms. And that's how you would read this. So if you had something that was black, brown, it would be 1, 1. Excuse me, it would be black. It would be brown, like 1, 1. And a third brown would give you 11 times 10 to the 1. That'd be 110. Now the gold, on the other hand, is 5%. This is really the company telling you, hey, this is a good resistor within to about 5%. So it's a tolerance, basically. You have 300 plus or minus 5% maybe. Silver is being 10%. Okay. So a resistor doesn't have to be just that, ooh, that's nice. A resistor doesn't have to be just the resistance of, or look just like that resistor that I just showed you. Okay, a resistor, I'm having trouble here. A resistor can be anything that gives resistance to wires. So anything that gives resistance to wires. So light bulbs are resistors, and motors are resistors, and we'll talk more about motors later. But anything that gets thrown into a circuit that impedes current is going to be a resistor. Even the wires. Wires are resistors themselves. And there's a really intricate way of calculating the resistance of a wire, and we may or may not get into that. We might not have time. So let's go through an example. We have a light bulb that is connected to a 1.5 volt battery, and the current in the wires is measured to be 0.15 amps. What is the current in the wire if the light bulb is connected to a 9 volt battery? So let's think about what we have. We have a voltage. We actually have two scenarios here, right? We have two voltages. One 1.5 volts and one that is 9 volts. We have a current over here, which is 0.15 amps, and we don't have any current over here. So what is the current in a wire if the light bulb is connected to a 9 volt battery? So we have this situation, and then we're putting it over here into that situation. Well, we can calculate one other thing that we have over here. We have a voltage, we have a current. We can calculate the resistance. That's not what I want. I don't want to be. Okay, we can calculate the resistance of the light bulb over here, and that would be voltage divided by current, right? V is equal to IR, or R is equal to V over I. So if we take 1.5 volts and divide it by 0.15 amps, hopefully you see that the resistance is just 10 ohms, right? Okay, take that, multiply by 10, you get 1.5. So the resistance over here is 10 ohms. Now the resistance of something doesn't change very easily. We can make it change if we increase its temperature and things like that, but we don't have to worry about that here. So if we have 10 ohms of resistance, then that's going to get thrown over here. And as a resistance for the 9 volts, we're not asked for resistance, we're asked for current. So if we have voltage and we have resistance, we're looking for current over here. How do we find that? Well, if we're looking for current, that's going to be equal to V divided by R. So if the voltage is 9 volts and we're dividing it by 10 ohms of resistance, then what is that going to be? Well, that's going to be 0.9 amps. So the current that we're looking for is 0.9 amps. Okay, so this is going to be a situation where voltage and current might change, but resistance never changes. Resistance is something that is inherent to the resistor or the light bulb or whatever. But the ratio of voltage to current can change, but it always has to have the same ratio of the resistance, 10. So let's talk about power. Power is something that we haven't really talked about in a while. Power was originally talked about as being, the equation was how much work you can do in a given amount of time. How much energy can you do per second or whatever. Or how much energy can you use per second. Well, here power is going to be slightly different. We have to put it in terms of voltage and current. So the equation is going to be volts times amps. Well, does this really give the same unit? What was the unit for power? The unit for power was watts, right? We had lots of laughs for that one. The what's the unit for power? So the unit for power is watts, but that's also a joule per second. So let's talk about this. A volt multiplied by an amp. Well, a volt is really a joule per coulomb. We got that from the last unit. And an amp is really a coulomb per second, right? When you multiply those together, the coulombs cancel out, and you do get a joule per second, which is in fact a watt. All right, so we are at least talking about the same thing. We're talking about the same unit of joule per second. And there it is in better handwriting. Now, we also have some ideas about volts and current in terms of resistance. So if you made some substitutions, here that that V is equal to IR, then you would get that power is I squared R. Now you could do the same substitution that I is equal to V over R over here and get power is equal to V squared divided by R. It's all the same power that you're calculating, just different ways of doing this. If you have current and resistance, you can calculate power. If you have voltage and resistance, you can calculate power. If you have voltage and current, you can calculate power. Doesn't matter what you have. You should always be able to calculate power.